Hi guys, today I'm going to be kind of recapping the topics of salts and introing ice tables. So kind of going through 2.03 and 2.04 just a little bit to kind of help hopefully supplement the things we've done in class. So this is from 2.03, so if you want to follow along, I'm going to kind of talk about why salts can either be neutral, basic, or acidic, and hopefully make a little more sense of it for some of you that are confused. So let's go right through it. The first one here is NaCl, sodium chloride. Okay, the sodium ion comes from sodium hydroxide. Okay, now because sodium hydroxide is a strong base, what that means is that that sodium ion is going to be a ridiculously weak acid. So in other words, it's so weak that water is actually a stronger acid at that point. So that sodium ion has no acidic properties. Okay? Now, if we look at the chloride, that chloride comes from HCl. Again, HCl is a very strong acid. So in other words, the chloride ion, being its conjugate base, is a ridiculously weak base. So weak that water is actually a stronger base. Now, what that actually means is that that chloride ion has no basic properties. Okay. Now, I skipped over the part whether or not this thing is a salt. Essentially, if you have an ionic compound that isn't already an acid or a base, it's a salt. Okay. So yes, this is certainly a salt, for example, number 1. Now, if we look at the acidic part, it's not acidic. If we look at the basic part, it's not basic. So if it's neither of those two things, it must be neutral. Okay? So as we go through, essentially we're going to break all of these salts in half. We look at the cation, consider what base it came from. We look at the anion, consider what acid it came from. When cations and anions come from strong species, they will have no effect on pH. When cations or anions come from weak species, they will have an effect on pH. So let's look at the second one. That's barium nitrate. So in barium nitrite, if I look at my barium, that comes from barium hydroxide. Barium hydroxide is strong. Therefore, that barium ion will not have any effect on pH. The nitrite comes from nitrous acid. Nitrous acid is weak. Now, that anion coming from a weak acid is the conjugate base of that weak acid. And because it came from something weak, that conjugate base will actually have basic properties. So, is the other part basic? Yes, it is. What that gives us then is an overall salt that does have basic properties. Number 3 is ammonia. Ammonia is not a salt. It's a base. So is part of it acidic? No. Is part of it basic? Yes, that's literally what it is. And therefore, it's just basic overall. Let's keep going. The next 4. The first one up there is perchloric acid. Perchloric acid is obviously just an acid. Is this thing a salt? No. Is it acidic? Yes. Is it basic? No. It's an acid. Okay. The next one, lithium carbonate. Now we're back to salts. Yes, this thing is a salt. It's an ionic compound. We have to observe where the two ions came from. So lithium comes from lithium hydroxide. Strong base. Therefore, the lithium will not affect pH. Carbonate comes from carbonic acid. Carbonic acid is weak. Therefore, that carbonate does have basic properties. And overall, this thing is basic. The next one's a little funky. The next one, we've got that weird ammonia looking sort of thing. So what that is it's an organic base. Okay, now you don't have to really know what organic base means, but if you see carbons and hydrogens and nitrogens, and it kind of sort of looks like an ammonia species, treat it like exactly like it's ammonia. Ammonia is a weak base, so anything that kind of looks like it will also be a weak base. Now, if you're looking closely, though, we also have an iodide there. So this thing is a salt, and essentially the first part of that, the CH3NH3, is more closely related to ammonium, like NH4 1+. Okay? So the first piece there, the CH3NH3, is basically ammonium, coming from ammonia. Ammonia, or any weak organic base, okay, are weak. So, in other words, its conjugate would be acidic. Iodine, or iodide, comes from hydroiodic acid. Hydroiodic acid is strong, therefore the iodide won't do a thing to the pH. It is not basic, and overall we have an acidic salt. The bottom one here is another organic base. A little more difficult to see this time, but we have that nitrogen, we have carbon, we have hydrogen, and there's nothing else there. So this is essentially going to behave like ammonia as a weak base. Is this a salt? It's not. Part of it's basic? Yes. No, it's not acidic. It's a base. Okay, that one's a little sneaky. Let's keep going. Sodium sulfite. Again, let's observe where these ions came from. Sodium came from sodium hydroxide. Sulfite came from sulfurous acid. Sodium hydroxide is strong, therefore it's not going to affect pH. So yes, this is a salt. No, the cation will not affect pH. Sulfurous acid is weak, therefore sulfite will affect pH, and it's the conjugate base of the original acid, so yes, it has basic properties. And then the overall salt would be basic as a result. The next two are where it gets confusing. In the next two examples, we have ammonium cyanide and ammonium acetate. Ammonium cyanide, both of those ions come from weak species. We have ammonium, which comes from ammonia, and we have cyanide, which comes from hydrocyanic acid. Both of those are weak. So that means my ammonium and my cyanide are each going to have acidic and basic properties, respectively. So I have to go a step further to figure out whether this salt is neutral or acidic or basic. So yes, this is a salt. Yes, it has acidic properties. Yes, it has basic properties. But I'm not quite sure whether this is neutral, acidic, or basic yet. We've got to look some things up. So in the back of the book, we have appendices. Appendix 22, Appendix 23. If you look up ammonium in the back of the book, you can find that its Ka value equals 5.6 times 10 to the negative 10. Okay? That tells us the strength of that acid, essentially. Now we have to be able to compare that to the base strength of cyanide. So we need the Kb value for cyanide. So, if I go to the back of the book and look at my Kb table, I don't see cyanide there. We have to do it indirectly. We have to do it in a different step. So, what is there is the Ka value of cyanide ions conjugate acid, hydrocyanic acid. So if I use that Ka value, I can eventually solve for the Kb of my cyanide ion. So the Ka of hydrocyanic acid is 6.2 times 10 to the negative 10. I can use the equation in our equation sheet that says that Kw equals Ka times Kb. Kw is a constant, 1.0 times 10 to the negative 14. Ka is what we looked up. And Kb is what we're solving for cyanide. So we rearrange that, we do a little bit of algebra, we get Kb equal to, and I'm going to plug it in. So I take 1.0 times 10 to the negative 14th divided by 6.2 times 10 to the negative 10th, and I get 1.6 times 10 to the negative 5th. So I compare those values. I have this Ka for ammonium down here. I have this Kb for cyanide up here. Those are the two things that make my salt. Which of those values is bigger? The base value is bigger, Kb. So in other words, overall, this is a basic salt. That's a lot more work, and it can be very tedious to figure out whether salts are acidic or basic when both of your ions come from weak species. There's one more. Let's go through that. I'm going to erase a little bit, and then we'll get started on that one. So for this last problem, we have ammonium acetate. Much like the previous example, ammonium acetate, both of these pieces come from weak acids and bases. So ammonium is going to come from ammonia again, and acetate comes from acetic acid. Okay, is this thing a salt? Yes, it is. Ammonium coming from that weak base is a conjugate acid, and it does have acidic properties. Acetate coming from a weak acid does have basic properties. And again, we're at an impasse. We have to solve for this thing now. Okay? So ammonium, we have the Ka from the previous problem. We know that's 5.6 times 10 to the negative 10. We just looked that up. Acetate, again, is not going to be able to be found in our Kb table. So we have to indirectly solve for Kb. We have to solve for it using the Ka of acetic acid. So if we go to the back of the book, Appendix 22, and find acetic acid, we see that it's Ka equals 1.8 times 10 to the negative 5th. And this is for acetic acid again. We have our expression, Kw equals Ka times Kb. We know Kw is a constant. We can plug that in. And we can solve for Kb. We solve Kb for acetate, and what do we find? It equals 5.6 times 10 to the negative 10. And this again is for acetate. We compare the base strength of acetate with the acid strength of ammonium, and they're the exact same number. So even though these two ions come from weak species, they have the exact same strength of acid and base, meaning the overall salt is actually neutral. And I'm all done for the salt video. So hopefully this was helpful. And again, I'm going to post another video that also relates to ice tables and getting ice tables started.